Hello, I'm Dr. Nagnath Hulle. In this video, we will try to understand the analysis of transient response of RL, RC and RLC series circuit. To begin with, uh, the transient and steady state response. Now here in this case, the output response of any system is divided into the two parts. The first part is transient response and the next part is the steady state response. During the transient response, the output is not stable and it goes to the transient period, and this period is a transient during which the output response of the system is varying, and after certain time it comes in the tolerance band or it becomes stable. That particular period of the system is known as the steady state response of the system. Now here, before going for the analysis of the transient response of the RLRC and RLC series circuit, first we have to understand about the initial and final conditions of the network elements. Now here, in this particular slide, we will try to understand the initial and final conditions of the network, and we have certain assumptions. Now here, first assumption is that at the reference time t is equal to 0, this is the reference time, the network condition is changed by the switching action. Means we are changing the switch from on to off or off to on. That particular instant of the time is the t is equal to 0, that is the reference time. The second assumption is that here we are assuming before switching the circuit was at the steady state. Means if we are switching the switch from off state to on state, here we are assuming that switch was in the off state for a long time and the stable state was reached. Similarly, when the switch is in the on state, it is in the on state for the long time, and in that particular case the circuit was in the stable state. This is the assumption. Means before the switching action, the previously circuit was in the stable state. Similarly, the network condition before t is equal to 0, that is when the t is less than 0, means before the switching condition, it is known as a final condition of the network, because before switching the circuit was in the stable state and the final condition of the network was reached. Similarly, the network condition at t is equal to 0 is known as the initial condition of the network, because just after the switching. Here we are interested in the network condition after t is equal to 0, that is for t is greater than 0, and before reaching to the steady state, that is nothing but we are interested in the transient response of the system, as we discussed in the previous slide. Here we are interested in this period after switching and before reaching to the steady state or stable state. That response we are trying to analyze in this case. Now here, to begin with, initial and final conditions of the network elements. Here, first network element is the resistance. In this particular case, before switching it acts as a resistor, and after switching it acts as a resistor, because this element is not the energy stored. Its performance or its behavior before switching and after switching is the same. Now here, whenever we are taking the case of the inductor, now here the final condition, that is before switching, it was reached to the steady state, and in the steady state or in the final condition it acts as a short circuit, and in the initial condition it acts as a open circuit. I will discuss this case first and then I will come back to this original slide. Now here in this case, if we are taking the case of the inductor, the voltage across inductor is given by the expression, that is VL is equal to L into di by dt. At the steady state, the constant current, that is DC current, is flowing through the inductor. Voltage across inductor is 0 because di by dt is 0. In that particular case, voltage across inductor is 0. And whenever the voltage across any element is 0, it acts as a short circuit. That's why in the steady state, inductor acts as a short circuit. Similarly, at the time of switching, that is at t is equal to 0, the di by dt is large because we are changing from the on state to the off state or from the off state to on state. In that particular case, di by dt is large. If the di by dt is large, in that particular case, voltage across inductor is large. And whenever the voltage across any element is a large value, in that particular case, that network or that circuit acts as an open circuit. Means here, as we discussed in this particular slide here, during the final condition, that is in the steady state, inductor acts as a short circuit, and during the initial condition, that is at the time of switching, the inductor acts as an open circuit. Now here, whenever the inductor is having initial charge I naught, in that case, how is its final condition and how is its initial condition? Here, the short circuit is a parallel with the current source of the I naught. This is the inductor having its initial charge I naught during the final condition, and it is just similar to the current source having its value of the I naught, that is in the initial condition of the network, that is just after the switching. Now I will come to the discussion of the capacitor. Now here in this case, the capacitor, during the final condition, capacitor acts as an open circuit, and during the initial condition, the capacitor acts as a short circuit. I will discuss its explanation and then I will come back to this particular slide. Now here in this case, the current flowing through the capacitor is given by expression, that is IC is equal to C into dB by dt. But whenever the current flowing through the any circuit is a maximum, it acts as a short circuit, and whenever current flowing through the any circuit is 0, then it acts as open circuit. Now here in this case, if we are taking the specific case, at the steady state, DC current is a DC excitation is available, that is the applied voltage is a constant, or output response is a constant. The dV by dt is 0, that is rate of change of voltage is 0. If the rate of change of voltage is 0, so the current flowing through the capacitor is 0. And if the current flowing through the any element is 0, it acts as an open circuit. That's why in the steady state, the capacitor acts as a, or in the final condition, the capacitor acts as an open circuit. Similarly, at the time of switching, that is at t is equal to 0, the dV by dt is large because we are applying the voltage from 0 to maximum or from maximum to 0. In that particular case, the dV by dt is very large. And if the dV by dt is large, so the current flowing through the capacitor is maximum. If the current flowing through the capacitor is a maximum, in that particular case, the capacitor acts as a short circuit. Now here I will go to the previous slide. Now here try to understand here. During the final condition, the capacitor acts as an open circuit, and during the initial condition, the capacitor acts as a short circuit, as I discussed in the previous slide. Now here in this case, during the steady state, it is open circuit, and during the switching time, it acts as a short circuit. Means here, during the initial condition, it is short circuit, and during the final condition, it acts as an open circuit. Similarly, the capacitor is having its initial charge, that is V0. How will be the case? In that case, during the initial condition of the network, it acts as a voltage V0 is in series with the open circuit, and during the initial condition, it acts as a voltage V0, that is capacitor should be replaced by that V0. So here, these are the initial and final conditions of the network, and we will use these initial and final conditions of the network to analyze the transient response of the RL, RC and RLC series circuit.